Okay, let's prove another fact about localization. Let's say we have a ring R and we have a multiplicatively closed subset S in R, and we look at the localization R localized at this set S. Then we have the following lemma. An ideal A in R, so an ideal of the ring, extends to an ideal in the localization if and only if R intersected S is empty. Proof. Let's start with the direction where we suppose that the intersection of A and S is not empty. So let small s be an element of A intersected big S. Then this element S divided by 1 is in R localized at S, and this of course has an inverse. Namely 1 divided by S. So this of course means that this element here, S divided by 1, so S divided by 1, which is an element of the picture of the image of the ideal A, which we write this way. This is a unit in R localized at S, and this means, of course, since this ideal now contains a unit, that it is all of A, all of R localized at S. So this is what we have, and this concludes part 1 of the proof. So for the other direction, suppose that this ideal is the same as the localized ring. Then since we have now all of this ring are localized by S, there exists A in R and S in S, such that A divided by S is equal to 1, because 1 is in R localized by S. And this means that there is a T in S such that a minus s times t is equal to 0. This is just going back to the definition of the localization. You remember this expression for the equivalence. So we have this, and we can of course write this in the following form. AT is equal to ST. But now look, AT is of course in the ideal A, because A is in it, and A times T is then also in this ideal A. But ST, which is equal to AT, is also in S, because S is in S and T is in S, and S is multiplicatively closed. So this is an element in the ideal A and also an element in S. Can conclude that that this intersection is not empty. So the intersection between the ideal A and S is not the empty set. And if you look at above what we wanted to prove, this is just what we wanted to prove, and this concludes this lemma.